Lesson 36, Section 3.5, Exponential Models, Part 1. The goal of this lesson is for students to be able to explore examples of exponential models. At the beginning of this chapter, we learned about half-life and doubling life and how to do those equations. So if you recall, this is the equation for doubling period, and this is the equation for half-life. A represents the initial value for both. The doubling period is determined by the problem, and the half-life period is also determined by the problem. Use the ideas that you were just reminded of to complete the following warm-up. Pause the video, complete the warm-up. The answer to the warm-up will be on the next slide. Here's the answer to warm-up number 1 worked out algebraically. If you did not get this answer correct, pause the video and write down the correct answer and steps. Use what you learned from warm-up 1 and the recall at the beginning to answer the following warm-up problem. The next slide contains the answer to the warm-up. Since we solved the last warm-up algebraically, this one we will solve graphically. You need to put into your y1 this side of the equation, and then you need to put into y2 the other side of the equation. The goal is to find the intersection. Now, these were my windows. I played around with the windows until I got there. The y min needs to be sure to include 1 million. I did 2 million. And then the x min and max you have to play around with. I started with 0 to 100. It didn't show up. And then I went 0 to 500 and it showed up. Then to get the intersection on the calculator, you hit second, trace, intersection, which is number 5 on the calculator, and you press enter 3 times and it'll give you the intersection. Since this is the intersection is 378 and 6/10. That means it's 378 and 6/10 minutes until there are 1 million E. coli bacteria in the petri dish. One of the models we're going to explore today are exponential growth and decay models. When a real-life quantity increases or decreases exponentially by a fixed percent each year or another time period, the amount y of the quantity after t years can be modeled by the equation y equals a 1 plus r to the t, or exponential decay y equals a 1 minus r to the t. A is the initial amount for both of them. R is the percent increase or decrease in decimal form. In decimal form is very important. R plus 1 is the growth factor, or R minus 1 minus R is the decay factor. So for example, if your initial value was 50 and your percent increase was 3%, your equation would be y equals 50, 1 plus 0.03 to the t power. By the same token, if your initial value was 50 and it was a percent decrease of 3%, your exponential decay equation would be y equals 50, 1 minus 0.03 to the t power. Another exponential model is compound interest. Now, you learned about simple interest in previous math classes. Simple interest ignores the effects of compounding. The interest charge is always based on the original principal. So interest on interest is not included. That's a topic that you did in Algebra 1 and previous math classes. We're going to discuss compound interest. Compound interest is interest paid on the initial investment, called the principal, and on previously earned interest. We can compound quarterly, annually, daily, and there's even more than that, monthly, yearly. There's a bunch of different ways. The formula is as follows. P is your initial amount of money. R is the percent interest that you're given. N, and this is the same N, is how it's compounded, and T is your time period, almost always in terms of year. As we discussed in the previous slide, N means monthly, yearly, quarterly, and there's a bunch of different options. So if you look down below here, if it's compounded yearly, N is 1. If it's compounded semi-annually, N is 2. Quarterly, N is 4. Monthly, N is 12. Weekly, N is 52. Daily, N is 365. These are the most common ones used. A, I forgot to mention before, A is the amount of money you'll earn after a certain amount of years. We will use this formula a lot in the next couple examples. The last kind of compound interest is continuous compounding interest. Continuous compounding is when interest is compounded continuously. The amount A in an account after 2 years is given by A equals P times E to the RT. P is the principal amount, E is the number E, R is the interest rate written as a percent, and T is the time period. We often refer to this equation as PERT, which is an easy way to remember it. Example 1 is one of the examples that represents exponential growth. In 1970, the population of Kern County, California, where Bakersfield is located, was about 333,000 people. From 1970 to 2000, the county grew an average annual rate of about 2.4%. Since this is exponential growth, we're going to use the equation P of t equals A times 1 plus R to the t. Now remember, A is our initial value, in this case 333,000, and R is our percent, which is 2.4% in decimal form, which is 0.024 or 24 thousandths. We're going to plug all these into the equation. So P of t equals 333,000 times 1 plus 0.024 to the t. When you simplify and add, you end up with P of t equals 333,000 times 1 and 24 thousandth, all to the t power. The next question asks, how many people lived in Kern County in 1990? Well, if you recall, our original equation starts with years after 1970, which means t equals 0 represents 1970. Which means if we want to figure out what we need to plug into the equation, we need to do 1990 minus 1970, which is 20. So we're going to do P of 20 equals 333,000 times 1 and 24 thousandths, all raised to the 20th power. When we enter that into our calculator, we end up with 535,110 people. Because we're talking about people, we're going to round to the nearest person and not give any decimal approximations. The next question asks you to use your graphing calculator to estimate the year when the population of Kern County was about 400,000. So the equation that we're trying to solve is 400,000 equals 333,000 times 1 and 24 thousandths, all the way to the t power. To do this, you make one side of the equation y1 and the other side of the equation y2, and then you find the intersection. So notice in y1, I have 400,000. That's right there. And in y2, I have 333,000 times 1.024 all the way to the x power, because you have to do x in the calculator. which is right there. And then these were the windows. I used the graph that was provided to come up with reasonable windows. And then if you look at the graph, in order to find the intersection, remember you do second, trace, intersection, and press press enter 3 times to find the intersection. So they intersect at X is approximately 7.7 years. Now, as you recall, 7.7 years since 1970. So if we actually want to figure out the year, it would be 1977.7 years. So towards the end of 1977 is when, according to this model, the population of Kern County is approximately 400,000 people. We can use our knowledge of logarithms to solve this problem, the same exact problem algebraically. So recall, 400,000 equals 333,000 times 1 and 24,000th all the way to the t power. Now to solve this algebraically, we first need to divide by 333,000, which reduces to 400 divided by 333 equals 1.024 to the t power. Now we need to take the log of base 1 and 24,000ths of both sides. Once we've taken the log of both sides, on this side, the logs undo each other, and we're just left with t. And on the right side, we're left with log base 1 and 24,000ths to the 400 divided by 333. When we put that into our calculator, we get 7 and 7/10 years since 1970, which, as we know, is towards the end of 1977. This example explores compound interest. You deposit $4,000 in an account that pays 2 92/100% annual interest. Find the balance after 5 years if the interest is compounded quarterly. So because it's compound interest, we need to use the equation A equals P, which is the principal, times 1 plus R divided by N to the NT. Our 4,000 is our P. This is our rate, but we need to write the rate as a decimal. So 0.0292, which is 292/10,000ths. And because it's compounded quarterly, N equals 4. So we're going to substitute everything in before we deal with 5 years, which is our t value. So A equals 4,000 times 1 plus 292/10,000ths divided by 4, all raised to the 4t power. Now when we simplify this, we end up with 4,000 times 1 and 73/10,000ths, all raised to the 4t power. At this point, we're going to plug in 5 for t. So A equals 4,000 times 1 and 73/10,000ths, all the way to the 4 times 5, which is the 20th power. When we put that into our calculator, our final answer is 4,626 and 33 cents. Because we're dealing with money, you always round to 2 decimal places. The second question says, how many years will it take for the balance to get to 4,500 with quarterly compounding? So we're using the same equation that we figured out here, but instead we're looking for t, and we have the a value. We have the final amount we want. So we say 4,500 equals 4,000 times 1 and 73 10,000ths, all raised to the 4t power. So to solve this, we need to isolate the exponent like all log problems. So we divide by 4,000 and we get 1.125, which is 125 thousandths, equals 1 and 73 10,000ths all the way to the 4t power. Now we have to take the log base 1.0073 of both sides. So just like we solve other log equations, we're going to take the log of both sides, but the base is going to be 1 and 73 10,000ths. Inside, we have the same values that were right here and right here. And when on the left side, this is just a number that our calculator will come up with for us. On this side, when the logs undo each other, we're left with 4t. So 4t equals this log, 1 base 1 and 73 10,000ths of 1 and 125 thousandths. Now, the last thing we have to do is divide by 4. You're going to put this number into your calculator, and when you put that number into your calculator, you get approximately 4 and 500ths years. Okay? Since they didn't give you an original year, you're just going to simplify it. You can simplify it to 2 decimal places, 1 decimal place. That's a good enough approximate number of years it will take to get $4,500 in your account. For part C, they want to find the balance after 1 year if interest is compounded daily. So really the only thing that's going to change is our n value. N is going to be 365, where normal for the last problem it was 4. So what we're going to do is A equals 4,000 times 1 plus 292 10,000ths, all over 365, all raised to this 365 times 1. This entire number can we put in our calculator, and when we put it into our calculator, we end up with $4,118.52. Now the last question asks us to calculate the interest earned after 1 year with daily compounding. Well, we started with $4,000, and after 1 year with daily compounding, we end up with $4,118.52. So our interest is just the difference. So all we have to do is take $4,118.52 and subtract it from our initial amount, which was $4,000. And our total interest over that 1 year is $118.52. Our third example starts out with a different amount of money and a different interest rate, and it's going to ask us a variety of different questions. So you deposit $3,000, so this is going to be our p-value, in an account that pays an annual interest of 3 5/10%. So this is our R as a percent, and we're going to write it as a decimal. So R is going to be 35 thousandths. And then the first question says, what is the balance after 3 years compounded continuously? So since it's continuously, we're going to use the PERT equation. So we have to start with A. A equals P to the RT. So A equals P is 3,000, R is 35 thousandths, and T in this case is 3. When we plug all that into our calculator, we end up with 3,332 and 13 cents. The next question is, what is the interest amount earned after 3 years when compounded continuously? So since we started with 3,000 and we make $3,332.13, our interest is the difference between the two. So we take 3,332 and 13 cents and subtract it from 3,000. Our total interest earned over those 3 years is $332.13. That's a whole lot of threes. This next question asks us, how many years will it take for the balance to reach 3,500 if compounded continuously? So since we're continuing to be compounded continuously, we need to use our PERT equation. So from above, we know that 3,000 e to the 35 thousandths times t is our equation. Now we're going to plug the 3,500 in for a. So 3,500 equals 3,000 e to the 35 thousandths times t. Now this is an exponential equation that involves e. So the first thing we need to do is divide by 3,000, which isolates our e, our exponent. When we divide by 3,000 over here, we discover that the decimal is not a nice decimal. So anytime it's not a nice decimal, we need to simplify it to a fraction and leave it as that fraction. So it simplifies to 7/6. Now, because this is an exponential involving e, we need to take the natural log of both sides. So we're going to take the natural log of both sides. When we take the natural log of 7 divided by 6, that's just a number. And on the left side, we're going to take the natural log of e raised to the 35 thousandths times t. Now, when we take the natural log and an e together, they undo each other. So we're just left with 35 thousandths times t. And on the left side, we're left with the natural log of 7/6. So to solve for t, we just need to divide both sides by 35 thousandths. And when we enter all that information into our calculator, we end up with 4 4/10 years. You can go to 1 decimal place, 2 decimal places, 3 decimal places. At this point, it doesn't matter as long as you give a good approximation. Part D asks us, what is the balance after 5 years compounded semi-annually? So the only thing there's actually a lot of things changing with this. Our principal remains the same, our interest rates remain the same, but since we're dealing with semi-annually, we need to return to this equation. A equals P times 1 plus R divided by N to the NT. Since it's semi-annually, our N equals 2. So we need to just plug all the pieces in. So we have 3,000 times 1 plus 35 thousandths divided by 2, all raised to the 2. And since we're trying to figure out what t is after 5 years, we're going to replace that t with 5. All of this information can be just plugged into our calculator, and we end up with the balance after 5 years compounded semi-annual being $3,568.33. Part E asks, how many years will it take for the balance to reach 5,000 if compounded semi-annually? This is very similar to example 2, part B. I would like you to try to solve this one on your own. Pause the video, solve it, and then the next slide will have the solution worked out. Here's example part E worked out for you. Pause the video and fix your answer if you have made some sort of mistake. Our final example uses the same equation, but it asks, when will the balance double if compounded semi-annually? Since we deposited $3,000, doubled would mean we made $6,000. So we would have 6,000 equals 3,000 times 1 plus 35 thousandths divided by 2, all raised to the 2t power. Now we've already simplified this equation before, so you might have even skipped the step above and just had 1.0175 all raised to the 2t power. So how do we solve this? We divide both sides by 3,000. So we have 2 equals 1.0175 all raised to the 2t power. We need to take the log of 175 10,000ths of both sides. So here's our log of both sides. Log base 1.0175. And we have to do that of both sides. On this side, it's of 2. On this side, it's raised to the 2t power. These two undo each other, and so we're just left with 2t equals log base, which is just a number, divided by 2, divided by 2, and our final answer is t is approximately equal to 19 98/100 years. You've now finished the video. If there are any parts that you don't quite understand, you can go back and rewatch them.